Let's look at an object that's sitting on a ramp. I am very creatively going to make my object a box. And the first thing we always like to do when we encounter a new problem is we like to make a force diagram. So if we make the force diagram for this box, we know that there's a force of gravity on the box by the Earth. This box is sitting on a surface, so we know there must be a normal force. And remember, the mathematical definition of normal is perpendicular to. So this normal force needs to point perpendicular to the ramp. And then the force that is allowing us to stay on the ramp, because we're going to assume that this box is at rest, is the force of friction. There we go. Now the second step that we like to do after making that force diagram is we always like to write a net force equation. So we imagine a nice little y-axis on our drawing, and we imagine a nice little x-axis on our drawing. And we look at these three forces and we say, well, the force of gravity is just in the y direction, so that is going to stay the same. We don't have to do anything to it. But the normal force is pointed in the positive x and positive y direction, so we're going to have to break that up into components. And then the force of friction is pointed in the negative x and positive y direction, which means that we have to break that one up into components as well. And I don't know about you guys, but having to break up 2 out of 3 forces into components every time I see an object sitting on an incline, well, that's tough. I don't think I really want to do that. But you don't have to. We have a trick. And let me tell you what that trick is. We are going to use our knowledge that the normal force has to be perpendicular to the ramp, and the force of friction has to be parallel to the ramp. And we are going to align our x and y axis with that normal force and friction force. Because now when I look at my new, quote unquote y axis, so that was this one, our y axis, it is now perpendicular to our ramp, and the normal force lies right on that y axis. If we look at our new rotated x-axis, well, it is now parallel to our ramp, and the force of friction is right on that x-axis. The force of gravity is pointed in the negative y and positive x direction, so that means that this force will have to be broken up into components. There's our right triangle for those components. But that's the only one that has to be broken into components. So we've now gone from 2 out of 3 forces being broken up into components to now 1 out of 3 forces being broken up into components. And that sounds a whole lot better to me. So when we end up writing those net force equations, so net force in the x direction, that is going to equal our force of friction plus this x component of the force of gravity. In fact, because it's parallel to the ramp, some people call it the parallel component of gravity. And we can calculate that parallel component of gravity because we know that the force of gravity is the hypotenuse of this right triangle. And then through similar triangles, we know that whatever the angle of the ramp is will be the same as this upper angle of our FG triangle. So to express the parallel component of gravity, we could express that as Fg sine of theta. And since this object is at rest on the ramp, that has to add up to be 0 newtons. If we write a net force equation for the y direction, we've got the normal force in the y direction, and then we've got this perpendicular component of gravity. So if we wanted to describe that leg of the triangle, we would do Fg cosine of theta. And again, because our object is not moving, we know that those things have to add up to be 0. Let's do a problem with this so we can do a few numbers. A brick weighing 10 newtons sits on an incline of 30 degrees. The brick does not slide on the incline because friction holds it in place. Determine the magnitude of all forces acting on the brick. So I'm going to do the really quick names of the forces, since these names are going to be pretty much exactly the same as what you saw above. And now we're going to try to determine the magnitude of all forces acting on the brick. Now they've already told us one of those forces. They told us that that brick weighs 10 newtons, which means that the Fg on this brick is 10 newtons. If I wanted to figure out what the force of friction was on this brick, well, I just need to use my sum of forces in the x direction equation, which is the friction force plus Fg sine of theta equals 0. So force of friction plus, and our force of gravity was 10 newtons. We're looking at the sine of 30 degrees. They have to add together to be 0. So if we do the algebra, we find that the force of friction ends up being negative 5 newtons. To find the normal force, we can just sum the forces in the y direction. So that is the normal force plus Fg cosine of theta. So the sum of force, so we don't need that part anymore. Fn, and then I'm going to say, since we've tilted these axes, positive is down the ramp and off of the ramp. So this Fg cosine of theta is in the negative direction. So we're going to say Fn minus 10 cosine of 30 equals 0. So that way when we solve for our Fn, we end up getting a positive number. We end up getting 8.66 newtons as our normal force. So those are all the forces acting on our brick. Force of gravity is 10 newtons, force of friction is 5 newtons, and normal force is 8.66 newtons.